Hello, my name is Jacob Dreger. I was responsible for performing the force analysis of our scissor lift and designing the belt as well as video editing.
Hello, my name is Howie He. I was responsible for creating the CAD drawing of the scissor lift and designing the ball bearings.
Hello, my name is Randy Lammer. I was responsible for designing the ball screw and gear train for our scissor lift.
Hi, my name is Daniel Stepien, and I was responsible for the background research and compiling of the report.
Our other group member is Aaron Jansen. He was responsible for the tapered bearings on the ball screw and creating the cost analysis of the scissor lift.
So, for our group, we were tasked with the design and assembly of a material handling scissor lift mechanism. First design model reportedly dates to the 1920s, during the time that forklifts were invented, but it wasn't until the 1970s when they were first manufactured and hit the open market that they became a standard in lift equipment technology. In 1966, the first patent for a scissor lift design was granted to Charles Larson. As you can see in the design, it contains a simple platform which is attached by a basic scissor arm concept with a jack being utilized to provide the lifting energy on one fixed side. A roller is used on the other side of the bottom arm to move the extended arms to lift. Today, there are 5 main components that are commonly used in scissor lift mechanisms. 3 of the components were shown in the patent design, which include the platform, scissor arms, and the cylinders. A 4th component, the base, was technically used in the patent design, which consisted of a fixed connection bracket holding the cylinder in place, but advancements have been made over the years to provide better support. One component not in the original design, which has been implemented over the years, is the use of a power source. The power source, which can be also electric and or diesel, is used to regulate the fluid in the cylinder to descend the arm mechanisms at a reasonable rate.
For our scissor lift, the 3 components that we chose to design were the bearings, belts, and gears. This includes 4 tapered bearings, 2 pillow blocks with ball bearings, one polyamide A2 belt, 4 bevel gears, and 2 ball screws.
Since most scissor lifts operate on a hydraulic or pneumatic system, creating a mechanical lifting device posed its own problems. As such, we used the basic knowledge that to raise or lower the lift, the angle of the arms to the horizontal would have to increase or decrease. Knowing this, we originally thought about using gears that would drive a rack which was screwed to the front arms of the lift. When the rack moved forward, the angle would decrease, lowering the lift, and when the rack moved backwards, the table raised. However, since the rack would be extending outside of the machine's usual footprint, we determined this could be a tripping hazard for workers. As such, we decided to use a ball screw so the angle of the arms would increase or decrease as the ball screw was rotated in different directions. Knowing that the motor needed to operate on a low torque but high RPM, we designed the gear reduction system so the ball screw would spin at the appropriate speed for lifting to finish in roughly 30 seconds.
Here's our finalized design. The engine operates at 1000 RPM on a 10 centimeter pulley, which is then transferred to a 25 centimeter pulley using a 3-inch thick polyamide belt. The 25 centimeter pulley then drives a shaft at 400 RPM. This shaft is connected to a 5 centimeter bevel gear on either side. For the sake of modeling, the bevel gears were simplified to be the same size. The 5 centimeter bevel gear attaches to a 20 centimeter bevel gear. This 20 centimeter bevel gear then drives a ball screw at 100 RPM. When the ball screw turns, the scissor arm is either moved forward or backwards. And based on our engine speed, the lift would take roughly 30 seconds to raise from 0.5 meters to 1 meter. To secure the ball screw, 2 tapered bearings were attached on either side. Again, for modeling purpose, simple pillow blocks were used. To support the shaft in the back, 2 pillow blocks were designed. All these components were designed to lift a max load of 1000 kg for material handling purpose, and the length of the table on the top, which was used for force balancing, accommodates for the size of most pallets used in a wide variety of industries.
While this design may appear sound and logical to our group, there are surely some flaws that a more experienced engineer would be able to point out and correct. It's for this very reason that organizations like OSPE are important for new, old, and aspiring engineers alike. OSPE provides a place for people to share experiences and knowledge so young engineers can learn industry standards and avoid learning through trial and error. Reading and understanding the content in textbooks and classes may help facilitate learning, but being able to connect and receive mentorship from people who have first-hand experience designing brakes, clutches, bearings, flexible mechanical elements like belts, springs, and gears is another extremely important form of guidance for all engineers alike.